So, good morning, good day, and good evening, everyone. I would like to welcome you all to our today's webinar on leak detection in the automotive market. The title of today's presentation is Future-Proof Leak Detection Systems for the Automotive Industry. The event is scheduled for 1 hour. The presentation itself will take roughly around 45 minutes, and there will be a short 15-minute Q&A session afterwards, in which we would like to answer all your questions. The webinar is on a beginner's level. To raise a question during the presentation, please use the chat function and select Send Question to Staff. We are happy to answer them afterwards. Your presenter today is Dr. Philipp Schurig. He has been with Pfeiffer Vacuum since 2020 and is firmly rooted in the design of leak detection solutions for the automotive industry. He has graduated with a doctorate degree in physics and is currently working as a business development manager for leak detection system builders. I have the honor to be your moderator today. My name is Jonas Klöß, and I'm the application manager for freeze-drying systems as well as leak detection systems for the automotive industry. And with that, I would like to turn it over to Philipp. Philipp, please go ahead.
Thank you, Jonas, for this kind introduction. And also welcome to the audience. I'm happy to join you here today in our webinar. Before I jump directly into action, let me tell you something about the company's name you see in the bottom of the slide, Pfeiffer Vacuum. Who are we? So we are a company over 130 years old and setting standards in vacuum technology. We also invented the turbo pump. We have 10 production plants worldwide and are a leading supplier of vacuum solutions for generating, measuring, and analyzing vacuum. We have over 3,300 employees worldwide, which mainly are located in Europe, with 2/3 of this, 2,000 people working in Europe and Africa. The next is Asia with above 800 employees, and in America, over 350 employees. This divide for production, sales and service department, and also we have a broad range of distributors all over the world who cooperate with us to bring to you, our valued customers, our products. Our products, here only a small glimpse into our available technologies. We can have roughing pumps, high and turbo pumps, leak detection software technologies, pumping stations, as well as chambers and gauges to measure the pressure. But this is today not an advertisement for our product. It's about future-proof leak detection systems. So this should be all what I tell you today about the products we have. And what I will tell you today in the next 43 minutes is why leak testing in the automotive industry, what is tested, what is a leak, which method exists. After these basics, we'll jump into the two main questions: why dilution of tracer gas, and how to reduce the COO, the cost of ownership. Afterwards, we will shortly conclude the main things we said during this webinar, followed by the 15-minute Q&A session in the end. And now let's jump directly to chapter 1, why leak testing in the automotive industry. Here I want to tell you today 3 major reasons. For sure there are more, but these are some of the most important. Talking about reliability. The moment the customer is driving with his car on a road trip, on the Route 66, he doesn't want to have a loss of liquid or loss of air, to have to stop every 3 days on the gas fuel station to repump or refill the pressure in his tires, or to lose oil on the way, to have a fatal motor crash somewhere. So reliability is one of the major drivers for leak detection in the automotive industry. Another thing when talking about loss of liquids of the car is the environmental aspect, because all these fuels, talking for example of the AC in the car, refrigerant there has a real high global warming potential, so a huge impact on the CO2 and on the global warming. And the regulations get stricter and stricter here, which talking about reduced losses of grams per year. And with new technologies here, refrigerants, the limitations get to lower values, and to reach these, for sure, higher pressures have to be reached, or the surface tension is smaller of the liquid, so they can pass through leak channels much easier than the known solutions at the moment. But mainly, or maybe the most important reason is safety. Because when we want to travel with a car, I want to feel safe and not to have fear of losing my life when driving with the car. And for this reason, the airbags is one of the major safety issues or safety measures in the car. But one of the biggest callback actions in the automotive industry was caused by a malfunctioning airbag igniter. It ignited, yes, so the airbag blew up, but also the igniter exploded and perforated the driver with some small metal pieces. This is not really helpful. So that's also one reason why we have to have thorough leak testing here to ensure the safety and the lives of our customers. There are other reasons like quality standards, which have to be met in this industry. But these are the major three reasons I wanted to tell you about today. But talking about leaks, what in a car is measured or what is tested? We talked about rims. I mentioned this as an example of the airbag. Well, you see a sketch of a car with a lot of components, but this is not only all of them. There are over 30,000 components in a car. For sure, the screws are not leak tested in a car, but some of the tested parts are rims, the shock absorbers, the fuel system, the air conditioning, the airbag igniters, the brake fluid system for sure as well, and many more. And they're also not decreasing in the future, because with the upcoming electromobility, the number of tested components will rise due to battery and fuel cell electric components and propulsion in the road of propulsion. So it will get more interesting in the future. So yeah, a lot of solutions have to be found for these future technologies. And yeah, talking about leak testing, what is a leak? According to the DIN EN ISO 2484, a leak is a result of a defect or flaw in the wall. There is no such thing as an absolutely leak-tight object. This means on an atomic scale level, an atom can pass through a nearly perfect wall because its dimension is a factor 1,000 smaller. But this is not a leakage or a path width, which is important for the automotive industry. Still, a leakage is considered a hole or a crack in the wall, which enables a fluid or a gas to pass from one side of the wall to another side of the wall. And how can real causes for leaks look like? Quite popular or well known in the industry is here a casting cavity. With aluminum casting, we have here the possibility that cavities are introduced if the process is not very well defined or some faults happen during the casting. These cavities can act as a direct path for a leak from the one side to the other, and will cause the loss of air in case of a rim, for example. Welding imperfections is another reason for a real leak. If the welding is not done properly, we see here it can result in also again cavities, which result in themselves again in leaks. When setting up some fuel systems or the tank system or whichever hoses have to be connected, some seals at some point have to be used. And if these are not new or have reached some age, the surface can alter, and we see these cracks which appear on the surface of a seal. Depending on the pressure which is put onto the seal, this cracks can get larger, and in the end, depict a leak channel from the one side to another. As number 4, we see here an assembly error. When we have two pipings which are connected, we have an O-ring sitting in between. When this is not fitted correctly, we have here also a leakage created. Well, this is nothing in this dimension which will happen in a car, but again, if some two pipings have to be connected, there's some kind of fitting in between. And if this is not done properly, there can result a leakage at this location. But talking about leaks, they also have to have some units. And this is the first time today where we want to engage you with a small poll. Jonas, please
Yes,
continue.
I will launch the first poll of today's presentation. So we would like to know from you, which leak rate unit do you mostly use, or which leak rate do you commonly refer to? Millibar liter per second, Pascal cubic meter per second, cc per minute, SCCM, or grams per year. So just click on the unit that is most commonly used for you guys. I see already some answers coming in. It's actually quite, one answer is quite dominant here on the answers. I will keep the poll open for another 10 seconds, and then I'm going to share the results with you. Okay, so I think that is quite clear. Yeah, so the majority, 92% of all attendees actually refer to the unit millibar liter per second, which is, I would say, also the most commonly used, at least here in Europe. And this is also what we use here internally at Pfeiffer Vacuum most of the times. So thank you for that.
Yeah, thank you, Jonas, for this small recap of the poll. So millibar liter per second is for sure the common unit when talking about helium world in Europe, but talking about air, SCCM or cc per minute is also present. But I also want to introduce shortly, as I talked before, about the transfer of a liquid or a gas through a wall, the leak in case of a mass loss. So we see here we have a mass or weight which passes through this leak in a period of time, and the combination of this equation, gram per year or ounces per year, is the loss of refrigerant in 1 year. The difference to a gas throughput we see here directly. Here we have to include the pressure. The reason for this is liquids in general are considered non-compressible, so you cannot compress them, which is not the case for a gas. So these are compressible, so we have to somehow consider the pressure in the equation. This is the main reason the pressure is here. Then we have also the volume of the gas passing through, and again, like before, the period of time. When we have a view at the right side of the equation, liter per second, this is also a pumping speed of a vacuum pump, for example. And mentioned before, millibar liter, a millibar times liter, is an amount of gas as it's pressure dependent. And as we now have viewed the complete equation, we have a throughput of gas, an amount of gas per second. But how is this measured? Millibar liter per second is the unit. And now we want to have a short view into the leak detection methods which exist. And before doing so, another poll for you to answer.
Exactly, we have another poll, which I'm going to launch now. Which leak testing method do you currently use? The bubble test, pressure rise or mass extraction, pressure decay or microflow, tracer gas sniffing, or tracer gas vacuum? So please select one of these options. Yeah, and I see already quite some votes are coming in. Thank you for your feedback. I will leave it open for another 5 seconds. Okay, thank you very much. So I'm going to share the results with you. You can see them here, also here. I think most of the answers, yeah, it's quite dominant, the tracer gas vacuum. So the detection of leaks with a tracer gas, either hydrogen or helium, for instance. Okay, thank you.
Thank you, Jonas. This gives us insight that most of our participants here are quite common with the tracer gas world, and as it is supposed to be somehow when we want to talk about future-proof leak detection systems. However, we also want to have a short overview about leak detection methods available in the market, which is a quite broad range here. The leak detector tracer gas vacuum method, which most of you know very well, is the method which has the broadest range of sensitivity, about 10 times the 0 to 10 to the minus 11 millibar liter per second. And the other methods here have not such a high range of detectable leak rates. They go down to only 2 decades for sound or ultrasonic sensors. Pressure rise and decay, microflow, mass extraction cover some of the air-based methods, as well as the bubble test and ultrasonic bubble test, and yeah, so on and so forth. But we don't want to spend a lot of time here today because we want to focus a bit more on the leak rates or the methods which are applicable to the automotive industry, which we want to design and show here with the 10 to the 0 and 10 to the -8, and also for the integral leak test methods, we want to spend some more thoughts here. And this next slide shows you 3 areas. Basically, we have the microflow or the air testing range from 10 to the 0 to 10 to the -3 millibar liter per second. Then we have a mixed area, which as well helium as air-based methods are possible to get the result. And then at some point we reach the regime where the helium testing is mandatory, as otherwise we cannot measure the result anymore due to the limited sensitivity of the other methods. We see here a broad range of products, for example, wheels or fuel tanks or lithium-ion batteries, which are on the lower area of the mixed area. Fuel injectors, we have here the air suspension struts, which reach out into both regions here. So it's really a broad range, and this is only some of the parts which are tested. And well, you can reach or extend the helium testing area or the mixed area through tracer gas dilution, as at some point also the leak rate in the high range might result in a pollution of the leak detector. But when we are otherwise other way around, we can reach with the airflow method range in the mixed area when we use diluted gas, as we then have to use smaller leak rates. But this we will cover and focus in detail a bit later. Today we want to talk about the integral tracer gas methods. So let us just have a small view into the important tracer gas methods here, according to the DIN N 1779. We can differentiate here on these 5 methods shown here between the gas flow direction from the inside out to the outside in direction. Outside in means here the interior of our unit to test is under vacuum, and we go around with the helium spray gun around our part and try to locate the leak location with spraying helium amount on the surface. Then if we want to measure the other way around, so an inside-out measurement, basically the interior of the unit under test is filled with helium and in some way located at the outside. We have the sniffing method, which is only a localization method. So we go with a sniffer probe around our part and can exactly locate the location where the helium is coming out of the part, but not directly the correct leak rate, as a lot of factors like the movement speed of the probe, the distance to the surface, the ventilation in this area, all this plays a role if we measure everything which comes out of the leak or not. If we want to have a real integral result here, so the complete measurement of the part, we have to use an integral method, which are the B6 or the B3, so the vacuum method or the accumulation, which have the differentiation, which can be applied, for example, if the part to be tested cannot withstand a high delta P. So the interior of the part cannot be pressured much higher than the outer part. For the vacuum method, for example, we have a vacuum 1 millibar or lower in the chamber itself, and the part is pressured with 1 bar, 10 bars, 0.5 bar absolute of helium. So depending on the requirements of the part, we have a delta P which might be too high and result in an irreversible damage of the structure of the unit. Still, we have here the helium leaking out of the part, which is also true if we have an accumulation measurement. So here, the interior of the part is also pressurized, and the outer part is under ambient conditions. So we don't have a high delta P. In regards to vacuum outside, we have atmospheric pressure there. We have a sniffer probe. With the fan, we result in ventilation of a homogeneous gas mixture outside, and we can measure the rise of the concentration to identify the leak rate of the part. These three methods here, sniffing, accumulation, and vacuum method, we want to spend a small overview in for some minutes to see the differences. All of these use tracer gas, either helium, hydrogen, or a mixture. It can be a mixture of a helium with nitrogen, can be a mixture of hydrogen with nitrogen, or helium, hydrogen, and nitrogen. Depends on your application, what you want to do. Also, one of the first differentiators here is that the accumulation and the integral vacuum tests are considered quantitative. So we really have a number in the end, and for example, 5 times 10 to the minus 4 milliliter per second. And this is the total leak rate of the part which we tested. This is not true for the sniffing test, as we here only can localize it, and due to the reasons I mentioned before, not quantify the leak rate. Also, again, both of the left two parts are integral and the other not. Now, one of the most important things in the automotive industry is cycle time, because we have to meet the production requirements of the end customer. So we have to see that our process is really, really fast. And fast processes here are the integral vacuum test and the sniffing test. These are methods which need not a lot of time to identify either the location or the absolute leakage of the part. Depending on the pressure and the requirements of the part, the accumulation test is sometimes necessary, but due to the measurement of a concentration rise over time, this method needs some more time. So medium to long time interval is needed for cycle time. Another important factor sometimes are the investment costs and tracer gas costs. So for the integral vacuum test, these are the highest in terms of investment costs. As we need a vacuum chamber, we need a roughing pump for the vacuum chamber, some gauges, and this is driving up the cost for this solution. While for the accumulation or the sniffing test, we mainly need a sniffer probe to identify the location of the leak, or the sniffer probe and some hull or some chamber to cover around our part to be tested in the accumulation test, which induces less cost. So we are in the low to medium range here. For tracer gas costs, all of them are the same, because considering the one and the same part which we want to test with each of the methods, we need the equivalent conditions. So the same pressure in the parts, we have the same tracer gas costs. Also important is the sensitivity. So to which range or to which value we can detect the leak rates. And this is the highest for the vacuum test, as the surrounding of the chamber is on vacuum. So the helium concentration in the background is really, really low. When we do this consideration with accumulation and sniffing test, so the background here is defined through the ambient helium concentration in air, which is at 5 ppm. So here we're running into limitations concerning the background. But tracer gas costs we wanted to talk about. So these were the basics here. And now we want to jump into the influence of a diluted tracer gas. But why do we think about dilution of tracer gas? Or why is tracer gas a topic at all? Well, in the past, between 2006 and 2019, 3 worldwide helium shortages occurred. The shortage here means that not every customer was able to receive the amount of helium he would need to perform the tests or to produce like he was used to before. So some other ways had to be found, or the production was simply stopped. The total length in these 13 years where the shortages occurred was 7 years. So 7 out of 13 years, there were helium shortages around. One solution here would be to consider forming gas, as helium is 3 to 4 times more expensive than forming gas. Forming gas is considered a 95% nitrogen and 5% hydrogen mixture. This could be a real thought. And to be sure, just for you, modern leak detectors are capable to change between helium and hydrogen by a press of a button. So why does not everyone switch? Before we go into detail for this answer, we just want to have a short view on alternatives before doing so. For sure, you can always design your system to use 100% helium. So we have a leak rate of 10 to the minus 4 millibar liter per second you have to detect, as this is our requirement for the lifetime or the quality level we want to reach. And now we have to think about how we can save costs. Well, one way is to reduce the helium concentration. When we only apply 10% of helium mixture to the filling of the part for the leak detection, we can do this, but we now then have to consider that we have to detect 10 to the minus 4 millibar liter per second leak, as this directly translates to a lower leak rate. This is possible for sure when you design your leak detection system from the very beginning for this procedure. If you want to save costs at a later time in the given system, a retrofit or a consideration here has to be done, which is not always very straightforward. Here, maybe the second choice could be an option, a helium recovery unit. With this, you can recover up to 98% of the used helium in your process. This 98% depends a bit on the tightness of your helium system and also on the parameters of the recovery system. This is a complex product and not for everyone the right choice, because it's very costly in the purchasing, because we have high initial costs, but it will pay back through the reusage of the used helium. These are two methods, two ways to consider before you think about entering the world of hydrogen. But when we do so, what are the main drivers here? What are the things you find easily? Well, hydrogen is cheap, it's abundant, it has a low ambient concentration, it's only 0.5 ppm compared to 5 ppm of helium. What you also find out very quickly, and most of us also had in chemistry in the school, it's explosive. So when it reaches a certain concentration in air or with oxygen together, it can easily explode, which is not the best if you want to use your part or your machine in the future. So the question here is now, is it worth the consideration still? As always, there are advantages and there are difficulties. So let's first try to talk about the advantages. So it's available as a diluted standard. We have a 95% nitrogen and 5% hydrogen mixture. This is also according to a norm. It's considered non-inflammable. You can use this gas without any further safety measures in your machine. It also can be produced locally in your factory grounds. With the right product or right machinery you buy, you can produce this there, and you are even independent of a gas supplier. And depending on the electric energy you use, so if it's regenerative, it also can be considered a green tracer gas, as it has no cost for CO2 emissions. But for one or the other customer company, this might be interesting when they follow the path of the ISO norm to get a very green image in the industry or the end customer. But where there is the light side, there's also dark side. So there are some major difficulties when we talk about hydrogen as a tracer gas. For sure, we have a higher background. Well, I told you before that we only have 0.5 ppm of hydrogen, of molecular hydrogen in the ambient air. That's true. But we also know very well that we have humidity in the air, which is H2O when talking about chemistry. And this H2O is when this passes through an electric beam, so electrons can hit this molecule and cause water splitting. So we are separation of oxygen and hydrogen, and this created hydrogen can be measured within the detector. So we have artificially created high background here because of water splitting. And this water can occur from moisture, which is on the surfaces of your leak detection chamber. When closing it, it can be caused by outgassing, as in the first micrometers of the steel. Always hydrogen is present. It can outgas there, and this will also cause an artificial higher background in the beginning. So you have to use a lot of time to reduce the background in a vacuum method when talking about forming gas or hydrogen leak detection. Okay, we're talking about vacuum methods. How is it with sniffing? For a sniffing application, the hydrogen of forming gas is somehow a bit more interesting. But we have to consider here the dilution, which I mentioned on the left. We have to use it in a diluted form. So we also have a limited sensitivity because before we cannot see 100% of hydrogen, we only have to consider 5%. So we always have to calculate to a lower leak rate. 10 to the minus 2 gets to 5 times 10 to the minus 4. And at some point reach the background and the ambient air as well, which is also impacted of the factory surroundings, for example. Welding in the factory surroundings is often done by an argon hydrogen mixture, which pollutes the surrounding air, or when you charge your accus and batteries of your power tools in the factory, or your forklifts are electric, the charging also creates electric, not electric, but hydrogen. These are always causes of an increased background in the factory or of your leak detector. For sure, there are solutions or measures you can take. For example, in a separate room where you do the testing, where you have a fresh air exchange with the outside, so you reduce the impact of the factory to the room where you do the testing. All these factors here play into the limited sensitivity. So we cannot reach the broad range we have with the normal helium tracer gas, 10 to the minus 0 to 10 to the minus 11. It somehow stops in the 10 to the minus 6 range or 10 to the minus 7. But well, still, depending on your specific application, forming gas might still be a possible way to reduce your cost if it's applicable. This has to be foreseen in detail if your application or your product is can be used with forming gas. So the reduction here for your costs with forming gas is one way, but how can we reduce the cost of ownership of your complete system further? And here now we have another poll which want to ask you some interesting question.
Yes, I will launch it now. So this is the third poll of today and actually also the last poll of this presentation. How do you decide which equipment you use? So what is important to you basically? The installed base, the price performance ratio, the total cost over lifetime, the cycle time, or the purchase cost. So please select one. Okay, I'm getting some quite differentiated feedback here. It's good to see. Okay, give it another 5 seconds. Right, thank you very much. I'm going to share the results. So you see it's quite well distributed, I would say. Price performance ratio, total cost over lifetime, as well as cycle time are the most important factors. Installed base, close follow-up, and purchase cost at the, let's say, last position. Okay, thank you for your feedback.
Yeah, well, that's an interesting outcome. We will see soon how we could and can improve our cost of ownership. But before this, we just want to see the definition. What is the cost of ownership? So Wikipedia says here, the total cost of ownership is the financial estimate intended to help buyers and owners determine the direct and indirect costs of a product or service. What would be near for us to explain this procedure or this definition at an example in the automotive industry of cost of owning a car. So which costs do we face when we own a car? For sure, the purchase costs are the main driver in the very beginning, but then also the fuel consumption when driving around, the insurance we have to pay on a yearly basis, the repairs, the maintenance, and the taxes to the country are also some factors besides others which contribute to the overall cost of a car. To make this example easy, we only want to focus on the purchase cost of fuel and the maintenance cost in the example here. When talking about this example, we will use a use case that we will drive 15,000 kilometers a year in a 5-year consideration time span, and one tank filling costs $50. These two cars we want to compare here have purchase cost of $20,000 versus $12,000. and a fuel consumption of 5 liters versus 5.5 liters per 100 kilometer. Also, the maintenance costs are nearly similar with 1,000 per 25,000 kilometers or 1,100 per 20,000 kilometers. You see, when we look at the outer columns, it's not a big difference here. $4,500 versus $5,200 for the maintenance cost. The highest impact here is the fuel consumption. It's $187,000 versus $206,000. And if we sum this up to a total amount, we have $212,000 for the red car and $223,000 for the other car. So we see here that also only a slight increase in fuel consumption here can cause the change or the change of the cheaper car to the, in the end, more expensive car. But today it's not about talking about how expensive it is for us to own a car. It's about the major costs drivers of a leak detection system. As we are only a supplier of components, we cannot rate here or do not want to investigate the cost of an automation system or the product handling system. Here we can talk about leak testing instruments, the vacuum system, the tracer gas consumption, and the footprint and cooling water as some other factors which we will not discuss here today. Also, the leak testing instruments, the major drivers here are nearly equal in these terms, so we want to focus on the vacuum system today, as we already have talked about the tracer gas consumption earlier in this talk. So how can we save costs with a vacuum system? For this, we'll have a nearly similar investigation like in the example. We will have a view at the purchase cost, the power consumption, the oil need, and the maintenance costs of two different vacuum systems. These are seen here with a lifetime of 10 years, operating 24/7, which results in nearly 8,800 hours a year. For this use case, we use 20 cents per kilowatt hour as an electricity cost, and also one common oil price, 1 liter for $10. So we see a purchase cost. The left pump is double the pricing like the right pump, but for this we have a lower power consumption from the red pump. It's called red pump. This translates here again in a lower overall cost for the power, 5 liters per year as oil need versus 8 liters. Again, is not the high difference here as well as for the maintenance. 6,500 in total versus $8,800 in total. So if we sum this up, the total amount here, you reach $69,800 for the red pump and $85,000 for the blue pump. What tells us this? So the initial cost was, I think, the answer with the lowest parts here is not always the major driver to reduce the overall costs. Talking about the installed base, when you see new pumps coming up, also maybe it's considering to investigate the power consumption here, because you can save cost over lifetime when doing so. And in total, yeah, you see here the differentiation that energy efficient pumps can save you a lot of money. So let me conclude this talk to 5 points. One way to reduce costs is the diluted tracer gas, because cost savings by using lower concentration is possible, but also with a lower detection barrier. So again, the example was 100% helium is 10 to the -4, 10% helium usage for the very same leak challenge would result in a leak rate which has to be detected of 10 to the -5. A helium recovery unit is another way to save costs in the end, because high initial costs have to be made to save up to or recover up to 98% helium from the process. Depending on your measurement and on your part to be tested and the factory surroundings, hydrogen is also a green tracer gas alternative, which inherits strongly reduced costs, but it is more difficult in handling, and it has high importance of the surroundings. When you want to test with 100% of hydrogen, these costs are are somehow balanced out by a very strong increased safety measures you have to take, as it has to be made sure that it cannot inflame or explode. This would drive up the cost of ownerships when changing to hydrogen, but the main driver for total cost of ownership are often dominated by the ongoing expenses like electricity, maintenance, oil exchange. When talking about oil exchange, you can also see that often the oil is not considered a normal waste. It has to be disposed of in a special company, which increases here the cost even higher. And also the major driver to reduce the costs is the energy efficiency, because the energy consumption of the equipment inherits the highest potential for optimization, as the electricity is a major driver, like shown in our example before. But well, now, how does this help you to design a future-proof leak detection system? I want to try to answer this question with one sentence for you. Design the leak detection system to utilize diluted gas while using energy-efficient pumps allows to reach sharper future limits with 100% gas concentration. This means that if you see a leak rate X today, design a system with a reduced diluted gas to meet this specification using energy-efficient pumps. And if your product you test here is cause or potential for sharper regulations in the future, you can reach lower leak detection limits with increasing to 100% tracer gas. You already reached the background required for this, but now you really detect the sharper limit with the 100% gas concentration. And with this, I want to thank you for your attention. I'm curious to learn if you had some questions. And Jonas, now I will play back the ball to you.
Thank you very much, Philip. Thanks for this nice presentation. As promised, we will now go into the Q&A session, or at least this would be the plan, because I have not received any questions so far. So for the attendees, if you have any open questions, you can use the chat function of this software here. Please select send question to staff, and then you can reach us. There is one question coming. Does helium dilution need to be pre-mixed before the actual test?
I will clearly say yes, because if you think about just using the concentration of air inside your part and you put a volume amount of X of helium inside, you don't have necessarily a homogeneous mixture. So you don't know if at the location of the leak, really this mixture is present. So still you have to evacuate the inner part of your unit and then fill in the mixed helium dilution. So this way you can make sure that everywhere the same tracer gas concentration is present, and you measure and you calculated it correctly.
Yeah, so it's a recommendation. Okay, thank you, Philip. So far, there's no other question besides this one. So for all attendees, if there are any open questions, you can always reach out to us also after this presentation. You should receive a follow-up email in which you get the contacts of us, and then we are happy to answer all questions of you also afterwards. Okay, then I think we are good. Thank you very much for joining us today. Philip, thank you for this presentation. And yeah, I wish everybody a good day, and yeah, talk to you soon. Bye-bye.
Bye-bye. Thank you again.